In this video, we will be going over how to use LabVIEW classes to make a hardware abstraction layer. If you're not familiar with LabVIEW classes or hardware abstraction layers, then I suggest you go online and research what they are. They're very useful to use. In fact, I would highly recommend that every test system you use should use a hardware abstraction layer for its maintainability purposes. The brief 2-second summary of it is the idea with the hardware abstraction layer is you don't want your tests to be dependent on a particular set of instruments. For instance, you may need a measurement from a DMM, but you don't particularly care which DMM it is as long as it meets the specification for the measurement. So you may have a Keithley DMM, an Agilent DMM, or an NI DMM, all of which have good enough specs to make the measurement you want, but you don't necessarily, you want to be able to use all three if possible, especially as if you wanted to reuse the code elsewhere. You may have a different test platform with a different DMM in it, and you don't want to rewrite that code. So the idea with the hardware abstraction layer is that you write your tests such that when you want a DMM measurement, you call what we call the base class, the DMM class, and say, I want to take a voltage measurement. And then in the DMM class, depending on which child class you've instantiated, then it will either call the Keithley libraries, DMM get voltage function, the Agilents, or the NIs, depending on which one's hooked up to the system. So usually the way that this is set up, or the way I set these up, is we have a base instrument class. So this is the parent class of all of the instrument objects, and it has some basic methods in it to initialize the instrument, reset the instrument. There's a soft panel method you can overload so that each instrument type can provide its own soft panel if it's got a little bit of differences for it. And then I shim in a intermediate class level, which I call archetype. And archetype is your DMMs, your voltage sources, your switch matrices. All those are an archetype. So they get all of the goodies from the base instrument class that we write once and use a bunch of different places. And then they create a set of an API for that type of instrument. So the DMM base class would inherit from the instrument class, and then it would add get voltage measurement, get resistance measurement, get current measurements, etc., etc. And for usually on depending on which toolchain you're using for your intermediate archetype instruments, you don't have to put any logic that actually works in there. You could define just the API, or you could define a default API that should work in most cases. For instance, if you're used to using mostly Skippy instruments, you could implement the Skippy commands at the archetype level. And then if there was something in a Skippy instrument that was different, you would override that specific method inside the child instrument. Same with IVI. If you are used to IVI instruments, you could do the IVI calls inside your archetype, and then theoretically you wouldn't have to do it on any of your other child classes, though in practice I've rarely seen an instrument with a driver I didn't have to modify. So that's what we're trying to do. The big advantages of this, like I said, is code portability and reusability. We can write a measurement once and it's very clear what the logic is, and we get the logic right. We can even simulate what we're doing before we have hardware, and then when we go to transition to hardware, we then just instantiate the real classes and go from there. And if you're not familiar with what class instantiation is, it means that I'm actually creating a copy of the class and I'm starting it up, basically. One thing you need to be aware of if you come from a different programming language is that LabVIEW class programming is not class programming. It is object-oriented programming, but it is not like other class programmings. A few really interesting gotchas is, one, it is a pass by value class structure. And if you're familiar with other programming languages, you're probably going, what the heck right now? So basically you have a private cluster of data that contains the data for the class. This includes your instrument handles and any LabVIEW controls or property fields that you wanted to do it. And then it has type information that says, okay, I'm a Keithley DMM class. When you use it in LabVIEW, when you run the wire, you're running the private data over that wire. And then every time it hits a class VI, the class does something called dynamic dispatch. And what dynamic dispatch does is it says, okay, so I know I just received a class data, And I'm going to check, can I handle this class? And if I can, do I have an override method inside my class, or do I need to call the parents class for that? That means that allows you to write a set of APIs at the top level and then override them in the children like you would do in another language. And then in LabVIEW, the appropriate child or parent is called depending on if you've got overridden that method or not. One of the problems with this is that you got to be very careful with your class data, because if you fork the wire, then you've got effectively two instances of the class, including any sort of resource conflicts with that. There is a way to get around that, and it typically involves using something called a DVR. I'll probably do a video on how to use that, but it gets a little bit dangerous and it's more of an advanced topic. So let's dig into this. So I've already set up an instrument base class, and I'm calling this jmetestsolutions.instrument. Some of you longtime LabVIEW programmers will cringe. I am equally fluent in C# and the .NET languages as I am in LabVIEW, and I have an expired LabVIEW architect certification to give you an idea what my skill set's like. But I usually try and do the .NET conventions of doing a fully qualified path, which is why it looks a little bit weird. On the block diagrams, I kind of shorten the name sometimes because they can get ridiculous. But what I'm trying to do is create a chain of pedigree. So when you're looking at it on the file system or you've moused over it in the thing, you know where it comes from. And the way it goes is you've got your base, the manufacturer who wrote it, in this case, JME Test Solutions, what it is, and it's a .instrument. And then for my children class, after .instrument, I put .dmm or .power supply or .function generator or something like that. And then when we get to the concrete classes, you would be JME Test Solutions .instrument .dmm Keithley something or other. It'll go with that. One of the disadvantage of this, like I said, is that it's a bit ugly in LabVIEW. The advantage of it is that when you go through like a file listing, it sorts them in the file system pretty easily. So all of your DMMs will be grouped, modules will be grouped together, and all of your power supply modules will be grouped together. And when I'm talking about modules, I'm talking about packed project libraries. If you don't know how to make one of these, I've made another video elsewhere that shows you how to set these up. But my rule of thumb for Hardware Abstraction Layer is we want one class per PPL, and all classes are built into PPLs. And the reason we do this is for portability sake. So basically we'll write, and it also helps quite a bit when you have multi-developers working on the same code base, because since everybody should be running on PPLs except for the specific project they're working on, then they can't accidentally change a piece of common code. One of the disadvantages of this is it does make building a little bit more complicated. You have to be aware that if you change something, you have to rebuild everything that's affected by it. And for an individual concrete class, that's fairly easy because you build the one project and you're fine. If you change something in the archetype, you must rebuild the archetype and then rebuild all the children. If you make a change to the base instrument class, you must rebuild everything in order. So that means you would rebuild the base class, then you would rebuild the archetypes, then you would rebuild all of the children. If you don't do this, the code will probably still run, but your results will vary. You introduce some very interesting subtle errors when the parent library's version does not match what the child library was built against. You'll have to ask NI why that is. I still haven't figured out some of that. Another big advantage of this architecture is that each piece is only dependent on its parent. So for instance, if you have a concrete class for a DMM that requires a special like IVI driver, or it has a special toolkit, or you're using something out of like the NI-CAN libraries, which can be massive, or the NI-DAC libraries, you don't have to drag all that into every project when you're building your hardware abstraction layer. You just have to drag it into the one project you're working on. You build the PPL, and then you distribute the PPL. Once you distribute the PPL, it has all the files in it that it should need. Okay. So if you're not familiar with how to make a class in a PPL, it's pretty easy. You still have to have a root library. So this is just a LabVIEW library. You just do new LabVIEW library. And then in the library, we have one class. In this case, it's jmetestsolutions.instrument.labview class. I've left this common control in the library, so it's accessible in the PPL, but it's not part of the class. And I did that so that the children can use this as well. This one you'll probably not necessarily use unless you're using test-and. This is more of a test-and thing that I'm playing with. Okay, so inside your class, there's a few things you want to be aware of if you haven't used this as much. The class private data, this is just a LabVIEW cluster, so you can put in anything. You can put into a cluster, you can put into here, and it becomes part of the private data. Then I've created a class factory folder, and the class factory design pattern, if you search for LabVIEW class factory, a few white papers will pop up showing what you're doing. But basically the idea is that we want the base instrument class to be able to instantiate the children. If you're familiar with .NET programming, this is another programming language, is what we refer to as inversion of control, i.e. we're going to call the children objects and we're going to instantiate them, but we're going to rely on the children libraries to run their own init functions. So this thing doesn't need to know anything about its children. It just needs to know a config file and where the file is, or where the library or class file is that we're working on. It's not too bad to make a class factory. Basically what you have to do is inside, search for this get LV class default value object. And this is inside the functions palette somewhere. I always have to look it up. But what you have to do is you have to give it the file path to the class that you want. And then it gives you a generic object. And then you typecast that object into something more specific. In this case, itself. So we're upcasting the children class back up to an instrument class, which means you will not have any of the archetype functions. So you will not have access to get voltage or to get current or to set enable power supply, anything like that. It doesn't know about, it doesn't care about, it can't access. But when it's typecast to a base level object, then you get access to everything that the base class knows about, which is useful things such as initialize, close. I always do a launch soft panel so that you can mess with it, reset, things like that. And so we cast it to the instrument. Now, what's interesting about this is this doesn't actually change the data of the wire. It just changes the label of the data of the wire. And what I mean by this is that this object, when you start messing with it, it's still whatever the child class you've instantiated is. If you pass this into a function, it will call the children methods for that function, which is what we're doing in this case. I've personally, in this particular example, I've also built a little VI to get the path library correct. And the reason I'm doing this is if you're just running off of source code and you're just using a .lv class, it's fairly easy. You just point it to the class and instantiate it. If you're doing what I'm recommending, which is you need to have it built into a bunch of PPLs, we need to check to see if it's in a PPL, and then we need to modify the path so that we have a path into the PPL for the appropriate class. And that gets a little bit complicated, but I'm going to post this on GitHub at some point. So that's the basic class factory. Now, one of the problems we have with it is if you want to instantiate the object, every instrument has a unique set of parameters you need to run on startup, depending, what is your voltage range, what is your measurement accuracy, what is the power supply setting, is it enabled or not. And since the instrument class, base class, doesn't know about any of that, we're going to use a string filled in JSON strings for a config file. So when you look at my new method, the new method takes in a configuration in JSON, and it's got two pieces to it. It's got a header piece to it, which tells you the name of the instrument, the file that it is in. These can be relative path files, so relative to whatever PPL it was built in. And then one of the nice things about JSON objects, besides that they're simple strings basically, is you can put a JSON object as a field of another JSON object. So I have a config area, and in this case, there's just an example of some cluster data that you could put in there. In LabVIEW, they have pretty good JSON support now. They didn't used to for creating and manipulating these JSON strings. You can basically take most clusters and convert them to a JSON string pretty easily. A couple gotchas you'll get there is it only does basic types, and not all types will flatten down. So for instance, instead of paths, you need to give them strings, and you have to use double backslashes to comment out the backslashes. If you do use JSON for config files, there's something called jsonlint.com, and there's a few other validators out there where you can use that. If you have any JSON errors, if you were messing with it by hand, you can go there, or just write a little front end inside your children classes to manipulate its own startup config. Okay, so let's go look at that. So basically, for my new function, when I want to launch a new object, I parse the config header, and I only have to get just the header fields. I don't have to grab all of it. And in this case, I created a cluster to say, okay, inside this cluster, here's the 3 pieces I want, and I formatted them out. You can also use this array path to do it. It's not very good. There's a link on the functions palette to a toolkit that's much better, but it's also, you trade flexibility and functionality for complexity, and it was not needed in this case. This thing will compile on any LabVIEW platform built in the last 5-6 years. Okay, so first thing is from our config string, we grab their name, the file, and the type. Then we use the class factory to get an object. Then we ran the init function. And if you look at the init function, it doesn't have much to it. It's got configuration. We'll move that back. And it's just a stub. It's just an API. It doesn't do anything. In certain applications, it's useful to put a dialog box or something in here to say, hey, look, programmer, you forgot to implement this, or inform the user that the functionality is not was expected. Or if you want, you can also mark these as must overrides in the parent class, and then the child class won't compile until it has all of the must overrides implemented. I don't particularly like that option, because since you can't compile, you can't individually test the functions until all of them are implemented, which means what you're effectively going to have to do is all your must overrides, you'll just click on all of them and do create an override, and then it will create the VIs, and then you've got stubs anyway. So it doesn't do you much good. Okay. If you'll notice up here, the terminals have these little squiggly lines around them, and that means it's a dynamic dispatch terminal. And you can come down here. This connection is dynamic input required. All right, and we're going to save that. And because it's dynamic input, it's a dynamic dispatch input, what happens here is we instantiate a class object of the child instrument we want. When it hits init, if there is an init overridden inside the child object, it will call the child's method of that init, and then after it runs, it will then pass it out to this instrument, or this named cluster of instruments. Okay. So I've also got basic routines. The basic usage is you've got new, close, initialize, reset, and a soft panel. So I've already built this into my into a builds directory. So let's go look at an archetype. So here's the archetype, and this is what they should look like. Pretty simple, pretty basic. You add the PPL, not the source code, the actual built PPL to this project in the builds directory. And then you add your library, and you will be building it into a PPL. So one of the things you need to do is go to properties and go to additional exclusions. and make sure you exclude dependent packed libraries and dependent shared libraries if you're building the PPL into the same directory as its parent. I recommend you do that. It makes pathing a lot easier, but you will get an error thrown if you don't check those options. You also want to enable debugging if possible, and I will leave this on even in production. It doesn't really, like, it gives you a nice noticing. Disabling it does not really affect optimization and performance unless you've got like breakpoints set that ended up all the way down the line. But it does allow you, if something goes wrong, you can then walk through it on a production system if you have LabVIEW installed. All right, so when I created the class, if you go to properties for the class, you do inheritance. And I like the new wizard they have in LabVIEW 2020. When I made it, because I added my instrument PPL first, it found the instrument class and gave the option during creation to set the inheritance. And as you can see, top of the list is LabVIEW object, and then we've got the instrument base class, and then the instrument.dmm base class. While you're in here, you can also change the icon. So this will make all the VIs will have that header on their icon. And we'll apply it to all. I've only got one VI currently in here. And this is overriding the soft panel. If you can get away with it, it's best to override the soft panel at the archetype level, not at the concrete class level. And the reason is that if you've done it right, then your archetype API should be sufficient, that you should have one soft panel that will manipulate all the DMMs that you want for the functionality set you want. If you have a specific DMM that has additional functionality that shouldn't be in the archetype, you can override the soft panel in the concrete DMM, but then you're breaking part of the hardware abstraction layer, because any functionality on that soft panel you're using that's not in the archetype means that's a function you'll be using in code that's not an archetype function, and so you are directly linking your code to that specific model of instrument. And that's the whole reason that we're doing this is to avoid that. So what you'll want to do, especially this makes implementing additional concrete instrument drivers a lot easier, because once you've got the DMM soft panel done once, then you should be able to reuse it across the board. And then what you're going to do is you're going to use the launch soft panel VI from the parent to run this. Okay, save that. So this is a VI I use to launch the class factory launcher. Basically, what we're going to be doing is that you will load a config file, and then it will give you a list of which ones a drop-down list of all of the configs that you've got in that file. One of the other nice things I like about JSON is that you can put your JSON objects in a single file, one per line. And then when we parse them out or read the line, then each one we know is an entry we need to deal with. So in this case, I'm going to go into the config file and load up an example config. Press load. Come on. Oh, I haven't set that to run automatically. All right, we're going to load that. You'll see the dropdown says DMM, which is the name of the instrument. And then here is a config I can run with. And what this is saying is, here's the name, here's the relative path from the parent. So from the built PPL, here's the path to the LabVIEW class file. In development, I will point it directly at LabVIEW class files. In deployment, these config files are going to need to read LabVIEW libp, which is the PPL that it needs to look into. And then for type, you need to tell it which class it needs to look for. For LabVIEW class files, this type field is irrelevant because you've only got one option. For a PPL, you could have a dozen classes in there. I do not recommend you do that, but since it's possible, we're going to check for that specific class and go from there. and then we press launch. And you'll notice is that we've just launched the DMM soft panel from source code. So we launched this soft panel from the parent's launch soft panel option. And I can show you that too. It's set to floating. Okay. One sec. Okay, sorry about that. So I've set a breakpoint, open the block diagram, and I've set a breakpoint. So when I press launch, you can see that it went and grabbed the breakpoint. And we're going to refresh it and stop it. So that's the first high-level Firehose version of how to get one of these LabVIEW class-based hardware abstraction layers going.